Now you've had a chance to look at the problem. Let's think about it. At the left-hand side, I know the height and I know the velocity. On the right-hand side, I know the height and the velocity. So I'm going to compare the energy at these two locations. I think the energy is not the same because there's an outside force acting between these two locations. So to start with, I'll take a look at the total energy on the left side. And then I've got the accelerating force and the displacement both going in the same direction. So that means it's going to be work done by the car. So this is going to add energy to the car since work is done by the car. So I'm going to add the work of the engine. Now at the top of the hill, I have a braking force. This force is going to the left while the car drifts to the right. So the force and displacement go in opposite directions. So this is work done on the car. Work done on the car will be subtracted. So I'll subtract that from the initial energy. And then at the end, when I'm at the end of the run, I'll have whatever energy is left over. Next step, I'm going to start looking at the energies and see which ones I can cancel out. So at the very bottom on the left-hand side, I'm going to ask, is it moving at this point? And it is, at 7 meters per second. Then I'm going to ask, is it above the lowest height? And it's not above the lowest height. Between these two, it is the lowest height. So I'm going to get rid of the potential energy due to gravity. I'll leave the work alone. On the right-hand side, I'm going to look at the same thing. At the top, is it moving? Yes, it's 2 meters per second. Is it above the lowest height? Yes, it's 5 meters above the other position. So I'm going to keep those two energies. Next step, I'm going to throw in my formulas. So 1/2 mv squared plus the force of the engine times the distance of the engine equals the force of the brake times the displacement of the brake, which equals 1/2 mv squared at the top of the hill plus mgh at the top of the hill. Now I'll throw in my numbers. 1/2 995 kilograms times 7 meters per second squared plus 12,000 newtons times 11 meters minus the force, the braking force, which is what I'm after, times the 6 meters it acts across. All that is going to equal the energy at the top of the hill. So that's 1/2 995 kilograms times 2 meters per second squared times 995 kilograms times 9.80 meters per second squared divided by, or times 5 meters. Then when I set this up and do the math, I find out my force is 17,605.41667 newtons. Or if I look at the sig figs, I have two sig figs because of the 7.0 meters per second and the 2.0 meters per second and the 5.0 meters. You get the idea, two sig figs. So my final answer would be 18,000 newtons.